Okay, so let's start. So before diving into the lecture, wanted to go through a few things. So number one, some of you are asking about can you submit your homeworks on Friday a little bit later in your discussion section. The reason I specified it as 10 a.m. is so that the TA for the 10 a.m. discussion section can start going through the solutions and the homework. So which is why. So if you have a conflicting class or something, you can always submit a bit before. I plan to come into my office around 10 or so. So if you slip under the door, my office door before 10 a.m., I would get it. My assistant, Sandra, she arrives usually around 8 a.m. So she sits in the office suite right opposite the hallway from my suite. So you can always get to her. So there are plenty of options for you to kind of do it. You can always swing by the 10 a.m. discussion section and drop there if you so wish, but it's probably easier to slip under my door. Yeah.
So if we have the 10 a.m. discussion, we can't turn it.
You can turn it in there. Yeah, that's fine. Yeah. So basically, I just wanted the 10 a.m. discussion section to be able to go through homework solution if needed. Okay. The other thing is, some of you appear to hardly ever go to Piazza, and just want to let you know you are missing stuff there. And those of you who were yesterday, I mean, there's some excellent questions coming up as well as mistakes in my presentation. We pointed out, and so thanks for that. And I wanted to go through one of those with one student, I think Joseph, I think he kind of pointed that out, and which is that the book, and therefore me blindly following the book, didn't quite use the correct terminology for disjunctive and distinction and conjunction. So the slide I had presented, and this is what the book also follows, it basically says that the sum of product is conjunctive normal form, and conjunction means and the product of sum is distinctive normal form. In logic theory, that's actually incorrect. It's exactly the other way around. So the correct interpretation, therefore, is going to be so this is disjunctive. And this is conjunctive. Now, in engineering practice, we normally refer to as sum of product and product of sums. No one really kind of uses these terms much other than when you are thinking about digital circuits in a very formal fashion. But having said that, the lecture had a mistake, so you should use these terms. It shouldn't affect you because in the homework problem, I asked for both. The only thing is that I think this is problem 3 or 4 where I asked for both the two forms, and I gave 2.5 points for one and 5 points for the other. It would be 2.5 points for sum of products and 5 points for product of sums, because product of sums is harder. So just wanted to let you know of that. So that's one thing. Second thing is when we just call normal form, it actually refers to the top one, so it would be sum of products. Is there a question somewhere? No.
Are those two statements equivalent?
What do you mean by are those two statements equivalent? Which two?
Do they like have the same truth table?
Oh yeah, they will have the same truth table. They have a different equation form. But if you plug in the same values of the input variables into the two equations, you should get the same value as the output.
So if we want to go from conjunctive to disjunctive or the other way around, just to follow the and more?
Yeah, so I'll talk about it. So just wait, because some of the students who came to my office hours today, they were all kind of on that issue. Okay. Any other question?
Normal form is actually disjunctive.
Normal form is the disjunctive form by the correct definition, or in other words, normal form is the sum of products. Okay. So I would strongly suggest use sum of products or SOP and product of sum POS as kind of a normal value. Okay. And from this point on, if I ever happen to use or you choose to use, we'll use disjunctive for sum of products, conjunctive for product of sums, which is the correct definition. Again, thanks to the student who pointed it out. Okay. So that was on this aspect. Um, so the other thing I wanted to do over was to actually go over what was being asked just now. So how do we go back and forth? Okay, now last time we were doing the lecture, this was kind of the example at the way end where we had this function which was it had two minterms, 1 and 7. And remember, in the midterm form, in the sum of product form, these correspond to rows in the truth table where the entry was 1. Now, so we are already given the sum of product form. That's right there in the function description, and we had described how you can come up with a optimized implementation of it using that Karnaugh map. I'm not going to go over that again. What I want to focus on is that given that midterm for the 3 input function, I want to find the product of some form, max term form. Okay, so again, what we have is, so I'm given that's a function given to me, and it's basically saying for CBA equal to 001 or CBA equal to 111, the function is 1. And this is in sum of product forms. I want to find the product of some form. So what we'll do is, the trick out here is, and this corresponds to strategy 2 for Karnaugh map that I had described last time. What we're going to do is we're first going to find product of some form for the inverse of this function. So I want to write f prime in a sum of product form. Now f prime, the truth table, will have 1s wherever I had 0s previously and 0s wherever I had 1 previously. So its sum of product corresponds to, f prime sum of products corresponds to whichever entries now have a 1. So which would those minterms be? Firstly, how many of the minterms, f prime, how many minterms does it have? 6. That would be to the power n minus whatever I had in f, right? So it would correspond to m of 0, 2, 3, 4, 5, and 6. So it has 6 minterms, and it takes this particular form. And if I were to just expand this thing out, it's really m of 0 or m of 2 or m of 3 or m of 4 or m of 5 or m of 6. And now to get my product of some form, I'm going to invert both the sides, complement both the sides. So f is going to be whatever this term I had up there, complement of that. Okay, and now I go into my make use of my duality theorem. So m of 0 looks like a bar, c bar, b bar, a bar, right? That's m of 0. Now what duality theorem says is that and becomes or becomes and. So that's what we have to do. So let's, or De Morgan's theorem. So let's write it down. So what this would boil down to is, I have to say m of 0 complement and m of 2 complement and so on and so forth, m of 6 complement, or De Morgan's theorem, which is kind of specific case. So a plus a or b bar, a or b the whole thing complement is the same as a complement and b complement. That's what we're applying out here. Now, if you look at m0 complement, m0 was c bar, b bar, a bar, and I'm complementing it, so that becomes c plus b plus c or b or a, right? So this becomes, if I just focus on this term, it would be a term of the type C or B or C or B or A. And this is a max term. It's the bottommost max term. So it is M of 0, the big M of 0. So M0 complement is nothing but big of M of 0, and with the same pattern, it would be, that is what you will end up with.
Isn't it flipped around though?
Huh?
Isn't it flipped around?
Let's see. So M of 0 complement is C complement, B complement, A complement, the whole thing complement. That becomes C or B or A. That let's see. You have me. You are right. So okay, I write it as an expanded form. That's to avoid ambiguity. Okay, so this would write it like this: C or B or A, and M of 2 is 0, 1, 0. So that's C prime, B, A prime. I'm taking the complement of that. It would become C or B prime or A. So C or B prime or A, and so forth. And now you have your max term point. So strategy is that you take your original function, find its complement in sum of product form, and then take the complement of both sides. You will end up with the product of sum. And to go from given the function to go to its complement in sum of product form, you have to realize that all the minterms which are missing in my function will appear in the complement, because by definition. So complement of f would have all the minterms which were not present in f. So,
can you explain duality with minterm and max terms?
Duality, okay. So what does duality say? So dual of a function is I replace and with or with and. Okay. So let's say my function was A and B and C. Let's say this is my function. Dual of this function is A or B or C. Now the duality theorem says that FDABC is the same as naught of F over naught of A, naught of B, naught of C, which is the same as naught of. So if you look at this, so it's basically saying A or B or C is the same as naught of not A and not B and not C, right? So right hand side is complement of a minterm, left hand side is a max term. So right hand side I have the minterm not A, not B, not C, and if I take the complement of that, I'm getting a max term A or B or C, and that can apply for any particular pattern. Let's take another minterm. Let's take a minterm which is F equal to let's say not A and B and C. Let's say this is my minterm. So what's the dual of this? Anyone? Not A or B or C. Okay. Now what the duality theorem says is this equation. So we are going to just apply that. So that basically means not A or B or C is going to be equal to not of, and now I need not A, not B, not C plugged back into it. So A, B, and C, these things will get essentially reversed or complemented. So I have A and not B and not C. So what this is saying is that if I had a minterm A and not B and not C, and I'm going to take the complement of that, I'm going to end up with the max term not A or B or C. Okay, and the same pattern applies for everything. So, so once I get my complement function in a minterm form, and then if I complement both sides now, then I will get my original function, but in a max term form. So this is probably the easiest way to kind of approach this problem. So you start out again by given a function, you already have its sum of product. You express the complement of your function again as a sum of product, and that part is simple. Take all the midterms which were missing in the function, they will appear in the complement. Okay, because complement plus complement or the original function should result in true. Like all the midterms should be there. And then you kind of complement both sides, and you're basically applying a special case of duality. So I think the problem where I'm asking you to find both the forms, the reason, as you can see, the reason there are more points given for the product of some form is because you have to do kind of all this combination, where all this manipulation, whereas for the straightforward midterm form, sum of product form, you just have to kind of write it down. So that's relatively straightforward. Another thing I want to comment on was, which again came up in the, let's say I give you a, let's say I simply give you a, let's say I give you a function f let's say I give you a function f equal to a and b and d. And I tell you that this function, this system had 4 inputs, A, B, C, and D. And I want you to kind of give me the sum of product form, the normal form. So what I have out here is an implicant, but it's not a minterm because it's missing the C. So I now need to kind of generalize it, right? I need to kind of convert it into a minterm form. So the way to approach this thing is, I have A, B, and D, but I really want something which has C also. So one way of thinking about this is that I can write this thing as, this is the same as A and B and D and C or C bar, right? C or C bar is 1. And now I expand it out. I get A and B and D and C, or A and B and D and C bar. And now I have my term. So what's happening is that A, B, D was represent, the A and B and D was representing in a 4-dimensional terminology, it was missing one of the dimensions. So it was representing I had already grouped things together, but now I need to kind of take it out. It was representing, in our particular case, an edge, because it was missing one dimension. But to get both the points, the 2 points on the edges, I need to fill in the missing dimension. Now let's say I want to tell you this had 5 inputs, not just A, B, C, and D, but it also had an E. So now when I look at A, B, and D, it's missing C and E. That means it's missing 4 options, right? C and E can take CE, C bar E, CE bar, and C bar E bar. So now when you expand, you are going to take A, B, D, and then kind of handle all the 4 cases. So every time you have a literal missing from a product term like this, that basically means you need to consider both the cases. So if I have 2 literals missing, that means there are 4 cases. If there are 3 missing, there will be 8 cases. So you have to expand them out. So that's one approach. There's another approach which some of you found in the book, which is this so-called factoring approach. And you could certainly use that also, if you so wish. I didn't teach it, but if you adopt that and use it, that's perfectly fine. So it's in the chapter console, if you're not aware, you can kind of look at it. It's basically kind of just a stacking. Yeah.
And if I were to want to make that into sum of products, I would just take the duality of that.
No, you cannot take duality of this, right? I mean, again, you have to first find the complement of f in the product, in the sum of product. So looking at this, I know these two minterms are there out of the 16 possible minterms, right? Because I have 4 inputs, A, B, C, D. So the complement of this will have 14 minterms. I'll write that out, then I will apply duality. You see, if you apply duality straight away on this, it's going to give you a sum of, it will give you a product of sum for the complement. That's not going to help you. We want product of sum of the original function. So again, step number 1 has to be that you express the complement of your function in the sum of product forms.
So Professor, to find the complement, we just complement each element?
No. So this complement step, you have to do the special way that I'm saying. You have to write the complement in product of sum form as a sum of minterms, right? So the way to do it is look at what minterms are present in your original function. All the other minterms will be present in the complement. Okay, so in this case, the 2 minterms that are present correspond to A, B, D, C and A, B, D, C bar. So that's 2 out of 16 possible minterms. So your complement will have those remaining 14 minterms. So it will be a long function. Okay, but you should probably write it as like sigma notation. So again, for that very first step, okay, take the complement. Don't just complement it like that. You have to use this minterm.
But the sign doesn't change, it's your or together. It's your main.
Yeah, you are going to write f prime or f complement of f as a sum of products. But to think of complement of f as another function g. And the question is, what does its truth table look like? It will have entries 1 wherever my original table had entry 0, and it would have 0 wherever my original table had 1. So when I'm expressing this g as a sum of minterms, I'm going to look at those images. Now, this is a strategy for approaching this problem. There you can apply other ones also, but I think this kind of gives you a general recipe for doing it. Let's see, any other questions on this one before I move on?
If you have A or B, how do you find the
Huh?
sum of products? Would you have like A or B or D? How would you find the sum of products for that?
Or if you had A or B or D and you want to find sum of products of that, you can actually apply the same strategy. You take the complement, but this time around you express the complement in the sum of product form and then apply it to it. So try it. The only thing is, again, reasoning, thinking in terms of maths tends to be a little bit less intuitive because that's not how we teach it. But the process would be exactly the dual approach. Okay. Any other question? Let's see. So in the office hours, there was one other question which came up where one of the homework places I asked, give me a simplified Boolean equation. And I guess one student asked, what's the strategy that we can use? And the answer is there is no one strategy. In fact, it's one of those computer science problems which are intractable. That is, to find the best simplified equation, you really have to do an exhaustive search. So what I'm expecting of you there is that much like when you learned algebra in middle school, you're taught how to simplify algebraic equations, you kind of do the same thing out here. The problem is small enough that hopefully you will see some patterns, some symmetry, some sticking out and do it. There is no algorithm that I can give you which will guarantee give you the best result other than trying every possible combination. So again, so you may end up with different answers out there, possible, but you'll kind of look at how costly your answer is. So intuitively, your equation should end up looking simple. It should have few variables and few operations.
Can you assume, this is for problem 1 in homework, can you is basically equal to 0, and you want to.
No, remember in problem 1, what's happening is you are being given the decimal things. You are given the number 76, and you have to come up with bit 1, bit 2, bit 2.
Can you assume that 0 is basically 0, 0, 0, 0, 0, 0, 0, 0, 0, and then 1 is 0, 0, 0, 0, 0, 0, 0, 1, or something like that?
No, actually I'm not quite sure what you are saying. Again, you are not given 0 and 1. You are given 76, 74, 78. That's what you are given.
Yeah, but your output.
On your output, you have to, for each bit, you have to output. So you give me a function for bit number 1, another function for bit number 2, another equation for bit number 3, and so on. Okay?
Okay.
Any other questions? Okay. So let's move to next thing I want to talk about is this notion that how sometimes we deliberately pick a less efficient solution. And this has to do with the fact that the logic is implemented using real physical devices, and these real physical devices have delays in them. And that delays as in when you supply an input, the output appears after a short delay, not instantaneously. And that can cause problems. So I'm going to illustrate it by way of an example. So on the top, what we have is we have some system. It takes 3 inputs, A, B, and C. It's outputting the value F. And the truth table, Karnaugh map looks like what it is shown out here. Okay, so the function takes the value 1 whenever CBA are 0, 1, 1, or 1, 0, 1, or 1, 1, 1. But there are 3 ones in that. Sorry, there are 4 ones, and then it's also 0, 1, 0. So there are 4 different input combinations for which this function takes a value 1. Now, what we are given is so now imagine I'm a system, I'm feeding signals to it over time. So the waveform for A, B, and C looks like the way I have drawn. So when we start out at t equal to 0, A is 1, B is 1, and C is 1. What do you think will the output be? So A is 1, B is 1, C is 1. 1. So output will be 1. So we are going to start out with 1, right? Okay. Then after at t equal to 1, the C goes down to 0. So now my input is A equal to 1, B equal to 1, C equal to 0. What would the output be? Still 1, right? So what would I expect? I would expect that F should just remain constant, right? F should remain true at hold its value at 1. So this is what I would expect. F would look like this green line. It's 1 all the way through. Now, the reality is that's not what happens. There's some funky stuff happens when signals change. And they have to do with the fact that things don't change instantaneously. That is, when a gate sees its input changing, the output may take some time to settle. So now let's see why that issue causes problem in this particular circuit. So we go back to our Karnaugh map, and let's see how we would implement this thing normally. So to implement this thing efficiently, what would you do? So I've given this Karnaugh map. We have learned last time around that we want to have good sum of product implementation using this. So you have to kind of cluster things, right? Cluster things into bigger chunks. So what would you cluster in? Which minterms do you think you would cluster so that I have a good implementation? Do you want to take a shot? Let's start. Is there a cluster that I can form of size 8? No. What about size 4? No. Size 2? How many clusters of size 2? 3 of them, right? So I could cluster I have a cluster here, I have a cluster here, and I have a cluster here. So I have 3 clusters. Which one of them are essential? 2 and 3, okay, because that's the only one covering 2, and 5, 7. So those I have to select. So I have to select, let's see. So I have to select this one for sure, and I also have to select this one. And once I select these 2, have I covered all the ones? Yes, so I don't really need the third one, okay? So our implementation in this case is going to look like, so this, and if I make the circuit out of it, it will look like this circuit out here, okay? So I selected those 2, they correspond to implicants B and not C, and A and C, and that's the circuit that I have implemented. So that's how sort of we would normally design. And looking at this, if A and B were to be held at 1 and C were to change from 1 to 0 or 0 to 1, all that will happen is that the inputs to the OR gate will change from 1, 0 to 0, 1. But the output of the OR gate we would still expect to be 1. So that's the ideal case. Now the reality is not quite the same. So let's imagine these gates have delays. The electrical devices, they take some time to do their work. So let's say the delays are like this, that our AND gate, OR gate have a delay of 1, inverter has a delay of 3. Okay, this is a hypothetical example, doesn't necessarily correspond to anything with real delays being in this ratio. So let's say we have this situation, that AND gates have a delay of 1, OR gate have a delay of 1, and inverter has a delay of 3. What that means is, let's take the inverter. If I change the input signal to the inverter, then the output will also change, it will also toggle, but it will do so after a delay of 3. Likewise, if the OR gate input changes, and if it affects the output, then the output effect will be felt after 1 unit of time delay. So that's what we are given. Now let's try to work it out. So now what we are given is something like this. I have A, B, and C, and C changes value. And one thing you have to see is how I have drawn the edge now, kind of this sloping thing. And that also reflects the reality. Physical signals cannot change their values instantaneously. They take a little bit of a time to rise up or fall down because circuits have capacitors which take some time to charge up or charge down. Your physics classes, you would have done that. So in reality, kind of, you don't have these vertical edges. You have these sort of leisurely sort of falling or rising edges. So this is what things look like. Now let's do the following. What we are going to do is we are going to trace how Cn, D, and E, and F look like. So F is our final output. Cn is this intermediate signal. E and D and E are these 2 signals, and we are going to look at how they look like. So let's start with Cn. So Cn is the output of the inverter. So it would be the opposite of C, but with a shift of 1, right? Shift of 3, because the inverter has a delay of 3. So what will happen is that our Cn will look something like this, that at t equal to 1, C changed. When we started out, Cn was 0, the opposite of C, and then Cn will go high, but it will do after a gap of 3. So we see a delay of 3 time units out here. So Cn changes its state at t equal to 4. Now let's look at what D will look like. D is up here. So D is the output of its AND gate, and A is held constant, so A is always 1. The other input is C. C is changing from 1 to 0. So when I start out, what would D be? At t equal to 0, what do you think would D be? 1. And when do you think D will change? Because eventually C becomes 0, so output will become 0. So at what time would D change? at 2 because that has a delay of 1. So it looks like this. D changes from 1 down to 0, but it does so at t equal to 2. Now let's look at E. Now initially at t equal to 0, B was high and Cn was 0. So output E was 0. Now at t equal to 2, sorry, at t equal to 4, Cn changes and Bn is stable, so E will change. So when do you think will E change? So E at beginning is going to be 0, eventually E will become 1. At what time will E change? 5. So E will look like this. Okay. Now let's look at F. F is the OR of the two. F is the OR of D and E. When I start out, it's 1, D is 1, E is 0, so F is 1. In this middle region, here, it will see both D and E to be 0, and therefore there will be a short while that F will go to 0. And then eventually, it will again go back to 1. And again, we have to take into account the delays. So what F will look like is the following, that since the OR gate has a delay of 1, so when D changes, after one time unit, F will go down, and then later on when E changes, after one time unit from that, F will go up. So now F, if you look at it, it no longer stayed true all through. It had this little blip because of these delays. It's called a glitch in electrical engineering. So the signal, even though it was supposed to remain 1, saw a short time span of a transition happening. And that's not good because if, for example, F was feeding into a circuit which could look at it, happens to look at the F at the wrong time, then it will think F is 0, whereas it was never supposed to be 0. In some circuits, this glitching behavior may happen multiple times before the signal settles. So you may, F is supposed to remain 1, but it might kind of jump around a few times just for reasons like these before it stabilizes. Go ahead.
Is there a way to force a delay then?
Is there a delay?
Is there a way to force a delay in real circuits?
Force a delay.
Yeah.
What do you mean by force a delay?
So then they line up.
Oh, okay. You could. The problem is that we don't know very well how to design circuits with known delays. You can get them approximately there, but delay is not something to control very, very accurately. So, short answer, no, you cannot. Although, if we could attempt to solve this problem. So these glitches are bad. Okay, they're bad for several reasons. Firstly, I may happen to look at the signal at the wrong time. Secondly, every time a signal glitches, the capacitance on that wire has to charge and discharge. And again, if you go back to your physics, charging, discharging of capacitor means that you are going to have current flowing through some resistance in the rest of your circuit. That's going to burn energy. So every time you your signal transitions, it has a cost in terms of power consumption. So it's bad from that perspective also. Also, every time your signal glitches like this, it also causes electromagnetic interference elsewhere. So it's bad for that reason also. So it's good to not have unnecessary glitches. It can cause circuit to fail, circuit to be less efficient. So what could we do out here? Any thoughts on like how might I? So one suggestion was maybe I can add delays so that the signals line up. Okay, but as I said, unfortunately, we cannot do that. So is there some other way that you think we can keep F to be 1? So this is where kind of the trick that comes in is the following. I'm going to make the circuit redundant. So right now, OR gate is using 2 minterms. And what's happening is, one of the minterm was changing in one direction, the other minterm was changing in the other direction, and that's why we ended up with this glitch. What if we were to introduce one other minterm out there whose value remained 1 all through this change? And guess which minterm will that be? That would be our that vertical cluster that we decided not to use. Because if you look at when these outputs, when these inputs are changing from 1, 1, 1, which means I was here, to 1, 1, 0, which means I am at 6, which is, 0, 1, 1, which means I'm at 3, so here, right? So what's happening is I'm moving from 7 to 3 in terms of our input. So what's happening is this particular term, this particular product term, A and C, is going from 1 to 0, whereas this particular product term, B and not C, is going from 0 to 1. But if I were to also include this particular term, the one which combines 3 and 7, it remains 1 all through. And then I would not see this glitch. So if I were to have a circuit, which, let's see, which were to also include this third entry, which is redundant, I really don't need it if my circuit were to work properly, then I would be okay. So so I'll come to that. But these kind of glitches are called hazards. They are arising because of these timing problems. And in most cases, you would like to avoid them. In some cases, if you know what you're doing, it's okay. So we eliminate these hazards by introducing an additional AND term, an additional implicant. In this case, the one which is combining 3 and 7. And my circuit will now look like this. I have this extra AND gate, which corresponds to this green implicant. And now what will happen is, if A and B remains 1 and C changes state, then the output of this middle new AND gate will remain true at 1, and therefore all will remain at 1. So I will not see the glitch. Now, this is a very sort of simple, intuitive example. In more complicated circuits, these glitches arise in very complicated ways. And again, manually, it's very hard to deal with. So again, the design tools kind of systematically go and introduce some additional terms so that the glitching behavior does not take place. They do kind of an analysis of the delays, look at these things, introduce some additional terms. So it's adding cost to the circuit, but it's making the circuit better in the sense that it's less noisy, more robust, perhaps even more power efficient. So it's a simple example. We are not going to go into depth. Again, these kind of problems are algorithmically very challenging, and I mean, entire PhD theses and all used to be done just on these kind of things, come up with the tools. At this stage, there are companies, there are a small number of companies who are in the business of making tools which kind of just take care of all of these for you. So, so generally, as a digital designer, you sort of don't worry about these things if you're just using your tools. So only people who are in the business of writing those tools, in some senses, have to worry about that. So therefore, in this course, we will also not worry a whole lot about deeper techniques. So to summarize this particular module, then what we learned is how do we write K-maps or Carnot maps, how to find prime implicants, so kind of this clustering things. You can think of that clustering in terms of K-maps, or you can think in terms of our cubes. We saw how we can select the smallest number of prime implicants that cover all the ones, which take care of all the ones in our K-map. K-map can be quite painful for more than 4 variables. People can manually do for 5 and 6. The book shows how to. I don't expect you to know that. So there are algorithmic methods which then kind of work with these things. There's something called Cohen-Miklowski method, which used to be very popular in the 60s and 70s. Not very efficient, but that is what was used. Then towards late 70s, early 80s, a lot of research happened, and they came up with algebraic methods, so which directly kind of represent those Boolean equations and manipulate those, and that's what is now used by the tools. So some pretty sophisticated algorithms and all which sort of go behind. So in real life, software tools are pretty good. They can handle billions of gates. They'll probably take many, many hours to run, but computers are cheap and fast in them. Hazards are a problem. So, because now you are taking into account the real life delays of the circuit, so that complicates our task. So it's an even more difficult computational problem, but again, kind of tools do it for you. So, but the general strategy is that we add additional AND terms to our logic to kind of take care of that. Okay, so at this stage in the course, we at least know a way of designing combinational logic. The problem is combinational logic can get very, very complicated. We were dealing with functions with 3, 4 variables. What if you had 100 variables? Now you're looking at a truth table with 2 to the power 100 entries, or you're looking at a 100-dimensional cube. Very, very painful to deal with. So we are going to look at how we design more complicated things. So let's imagine you were designing a car. And if you had to design everything from kind of just basic pieces of metals and screws and all, it will take you ages to do it. So as engineers, what do? We rely on previously designed subsystems. So I design a new model of the car. I may borrow the engine from a previous car I designed, so that engine becomes, or I may decide to use a common, I don't know, seat mechanism across the different models of my car. So you start kind of developing a library of subsystems, and then you use those subsystems again and again in your design. So this is called modularity, or sort of you have a building blocks. Your building blocks are now more powerful, and now when you design your system, instead of designing your system in terms of the very basic primitives, you design your system in terms of these more complicated subsystems. In our case, what it means is that when you're designing a combinational logic, complicated combinational logic, you don't go down to AND gates and OR gates and inverters. They are too simplistic for our purposes. You think in terms of more complicated units, and then someone else, or perhaps you previously, would have designed those complicated units in a very optimized fashion. You will have a library of those, and you're going to use those. So that's the basic strategy that engineers always use to cope with complexity. That is, break down the problem into simpler pieces, and you make those simpler pieces reusable. In software, you have SDKs. You have libraries of functions, a math library, signal processing library, and then you write your code in terms of those. You don't necessarily go down to write everything from scratch. So the same concept out here, building blocks. What are the good building blocks for letting us design more complicated combinational systems? So that's the topic that we are going to do now. It's chapter 8 in the book. So that's just a recap. Okay, so this module, we are going to look at some of these subsystems, some of the commonly used subsystems. Now in Logisim, if you browse through the stuff on the left panel, you would see that there are a lot of other, in the library they have a lot of things available which we haven't talked about. Hopefully you saw things like mux and decoders, and things like that, or adders. These are kind of the subsystems that are often used as building blocks, as more powerful building blocks. We are going to look at decoder, encoder, multiplexer, arbiter, and comparator. Okay, some of these things have natural English meaning. Decoder, what does decode mean? I take something encoded and I am reversing the operation. Encoder is the other way around. So it takes many bits and encodes it into fewer bits. Multiplexer means I have a choice, one of many. I'm going to kind of select one of them. Arbiter in natural English terminology means that I am selecting between a bunch of competing things. So there are a bunch of things which are seeking attention, and I have to select one of them. And then finally, comparator compares. Is A larger than B? Is A equal to B? These kind of things. So we are going to look at these functions, and the idea is that generally now when you design stuff, you could use once you're designing more complicated things, you're going to be using, you can assume that these things exist and then design in terms of those, as opposed to going down to AND gates, NOR gates, inverter, XOR gates all the time. So that's the plan on this chapter. So let's talk about some of these. So firstly, recall when we were doing representations, we saw many different ways information can be represented. One of the ways information could be represented, and we had the example with the thermostat one, is the so-called one-hot representation. And what that means is, if I have a set with n elements, then I will represent an element with n bits, as many bits as the number of elements. And the idea is, one of those bits would be high, the rest would be 0, indicating, so for element number 1, maybe the first bit is high. For element number 2, the second bit is high, the rest are 0, and so on and so forth. So that's called one hot. So one of the bits is 1, the rest are 0. It was an example of one of our wasteful, redundant type representation. So in this example, let's say I had a set with 8 elements. If I were to do optimal, if I were to do kind of use minimum number of bits, I could use 3 bits and I could represent them as 0, 0, 0 through 1, 1, 1. One hot representation might represent it like this. I will use 8 bits, and depending upon which bit position is high, it would indicate which one of these 8 elements I'm selecting. So in the one hot representation, 1 and only 1 bit is high. So I need 8 bits because I had 8 elements. And if I were to think in terms of decimals, that's I'm going through 0 through 7. Now, what operations do you think are simpler done with one hot thing? What kind of things would be easy to do? Checking if what? Okay. Yeah, I can look at neighboring function. Yeah. Checking comparisons. That's easy. Although I guess that's equally easy in the other one if it is simply equality check. If you are checking whether something is larger or smaller, then it may be easy. What about what other things did you think of? What about binary operation? What kind of things? What are the benefits of binary? Add and subtract. Yeah, it depends. I mean, so in one case with the one hot, you have to shift the one somehow. In the other case, I can use the arithmetic operations. Well, in terms of storage, their pro and cons are certainly very clear. In case of one hot, I need a lot more bits. But if you look at one hot versus binary, there's another very significant advantage. Let's say I have 8 gates, 8 doors, and I want to control and open one of the doors based upon the input I'm getting. Each door, let's say, has some sort of a magnetic controller or something, and if I turn that magnetic controller on, the door will open. If I turn it off, door will close. Which representation do you think will work better? One hot, right? Because I can just wire it up straight up, right? I mean, to find out whether the ith door needs to be opened or closed, in case of the binary, I have to figure out whether the decimal value corresponding to the binary is I, right? Whereas with one hot, I straight away just look at the ith wire. So one hot has its advantages. It makes it very easy to know whether an input, which select of one particular value and kind of control some object using that. So one hot, oftentimes with kind of real hardware, when you are trying to select something, it's very beneficial. So our very first module is something called a decoder. And what a decoder does is it takes symbols from one encoding to another. And in particular, a very common form of decoder is that it will take a binary input and it will convert it into the corresponding one-hot representation. So the idea is that it's a box. It has n bits of input. So this symbol out here means I have a wire with n lines. Here I have a bit pattern which I would interpret as a binary number. So 0, 1, 1 means 3, 1, 0, 1 means 5, and so on and so forth. And on the output, I have a whole bunch of lines. And what I want is, if the input value is 101, then I want the fifth wire to be high. If the input value is 111, I want the seventh wire to be high, and so on and so forth. So I'm taking a binary representation and I'm going to convert it into a one-hot representation. And in a full binary, full decoder, if on the input I have n bits, then on the output, how many pins? I would have 2 to the power n, right? I have 2 to the power n possible values, and therefore each one of them would occur. So m in general is going to be much larger than n, and in the worst case, it could be as high as 2 to the power n. So that's what this box does. So if you're using, now the reason kind of this becomes an important one is because it occurs again and again in many more complicated digital systems. That you have to select something based upon a binary value. So what you do is you take the binary value, do a one hot, and then each of your wire will go to a different destination. That's what you want to design. And if I were to express it in kind of ordinary language, I would say binary input, if the binary input is A and one hot output is B, then we are saying B of I, that is ith wire of B, is 1 if A equal to I. That is, if the binary value represented by A has a value I. And so another way of thinking about it is, does anyone know what this symbol means? Less than? Shift, bit shift. Okay. Just used in C, Java, or bunch of languages. So what's doing is 1 shifted left by A times. So this would work for us. A has now a decimal value. So if A was 0, that would mean B equal to 1. So the rightmost bit of B is 1, everything else is 0. If A was 2, then B will get the value 0, 0, 0, 1, 0, right? So the second from the right bit would be high, and so on and so forth. So this operation is what the decoder is doing. It's taking 1 and shifting it A times. Now that's not how we'll necessarily implement it, but if I were to just ask you to kind of express it in software-like terms, then it would look something like this. Now let's see how we will implement it. So let's start with a very simple decoder, a 2 to 4 decoder. It takes a 2-bit A, and since there are, go ahead.
How do they represent shifted to the right?
Pardon me?
How do we just represent
Shift to the right? Anyone wants to answer the question? Shift to the right. Just stop with it.
Does it shift the arrow?
Yeah, the arrow is going right. Yeah.
Can you explain the shift again?
Okay, so what shift does is, let me go back to the previous slide. So let's say my computer had 8 bits. Then the value 1 is really nothing but value 1 is nothing but 0, 0, 0, 0, 0, 0, 0, 1. If I were to shift left by, let's say, 2, then that's what's happening is this one will appear here. I'll feed in 0 from this side, and everything else has shifted also. So that's shift by 2. Okay, so I'm going to here, and what I'm doing is I'm shifting by 2 here. Okay, that's what a shift operator does. What does if I think of these as binary numbers, let's say the first number, for a moment, let's imagine that this is a binary number and this is also a binary number. That is, think of its decimal values. What do you think a shift does in arithmetic terms? Huh? Multiply. Each shift by 1, each shift left by 1 does a multiplication by 2. So in this case, if you think of this 8-bit number as its decimal value is 1. I shifted by 2. The new number has a decimal value of 4. I shifted twice, as 2 times 2. This is purely a digression right now, but later on when we look at arithmetic operations, this gives you a clue. Multiplication can be done by shifting. Right now what we are discussing is that simply that we want to take a binary number and I want to map it into a one-hot coded thing. So let's look at how we might do this decoder. So we're going to start with a simple decoder, a 2 to 4 decoder. So it takes a 2-bit binary number, and since 2-bit binary numbers have 4 possible values, so my one-hot representation will have 4 values. So it's called 2 to 4 decoder. And in this case, A1, A0 are the 2 bits. They can take 4 values, 0, 0, 0, 1, 1, 0, 1, 1. My one-hot representation will have 4 bits, B3, B2, B1, B0, and we are going to map these things into one of the bits. So, for example, 0, 0, 0 would correspond to B0 being high, rest of them being 0. B1 corresponds to, A1, A0 corresponding being 0, 1 means B1 is high, rest are 0. And this and this. Okay, so that's what my truth table looks like. My truth table now has 2 inputs, A1, A0. It has 4 outputs, B0, B1, B2, B3. And the output B3 looks like this, 0, 0, 0, 1. Output B2 looks like 0, 0, 1, 0, and so on and so forth. Until now, we were looking at truth tables which had only one output. Now we are looking at truth tables which have multiple outputs. In this case, 4 outputs. So when I do Karnaugh map, if I choose to do that, then I will actually be making 4 Karnaugh maps, one for each one of the outputs. And I'm going to come up with a logic representation for each one of them. So that's what the truth table looks like. And if I were to implement it, it would look something like this. If you look at B3, its normal form says that B3 is A1 and A0. B2, its normal form is A1 and not A, and so on and so forth. And you would see that this logic is representing that. So B0 is an ANDing of not A0 and not A1, which is what corresponds out here. B1 is an ANDing of A0 and it's an ANDing of A0 and not A1. So that's this gate, and so on and so forth. So this thing is basically representing this truth table. It takes 2 inputs, A0 and A1, is making a one-hot output. So whatever is a binary value of A1, A0, that particular output number would be high, the rest would be 0. So 2 to 4 is easy. I can do the same thing with anything, 3 to 8, 4 to 16, and so on and so forth. Oftentimes in circuits we need the number of bits in A may be very high, like A may be 40 bits or some large number. Okay, and now you may be dealing with kind of complicated circuit, and kind of again designing them kind of becomes a problem. So one of the things, the way decoders are designed is you first design a smaller decoder, a 2 to 4, which is the simplest possible decoder. And then more complicated decoders, we design by using many of these simpler decoders. So you'll see how that is done very shortly. But this one was basically applying kind of knowledge from our previous chapters. So the question that we'll explore now is, can we make larger decoders from many small decoders? So let's say we want to build a 6 to 64 decoder. A 6 to 64 decoder takes a 6-bit input. A 6-bit input can take 64 possible values. So my one-hot coding will have 64 possible 64 bits. And what my 6 to 64 decoder would do is, it will, if like let's say all the 6 bits are 0, 0, 0, 0, 0, then the 0th output wire would be made high. And likewise, if the 6-bit input is all 1, then the bit number 63 in the output would be made high, everything else would be 0. So I can, if I were to ask to make a 6 to 64 decoder, one approach would be to make a truth table, but now, as you can see, I have a truth table which is 64 64 entries wrong and kind of starts getting painful. The other thing is that decoders are often needed in all size and shape. You may need 6 to 64, someone else may need 3 to 8, someone else may need 7 to 128, and so on and so forth. So it would be good if we had a strategy where I can make decoder of an arbitrary size from a small set of simpler decoders. So in this particular case, we will see how we can make a 6 to 64 decoder with 3 2 to 4 decoders and plus some other logic. That's kind of the basic idea that we'll follow. So let's see how that might happen. So each 2 to 4 decoder decodes 2 bits. So what we do is, remember, now in the 6 to 64 decoder, I have 6 bits coming in. Let's call them A0 to A5. And what we do is, we take 2 of them, so A1, A0, and we decode them using our 2 to 4 decoder. And let's call that output to be X320, 4 bits of X. Likewise, I take bits number 3 and 2 of A and also feed them to another 2 to 4 decoder, and let's call that output to be Y, again 4 bits of Y. And finally, let's take bit number 5 and 4 of A, feed them to a third 2 to 4 decoder, and I end up with 4 bits of Z. So let's say now we have done that. So what we end up having is, looks something like this. So for the final case, A5 and A4, it feeds into Z3, Z2, Z1, 0, and this is nothing but what we saw previously for the 2 to 4 decoder. Okay. Likewise, we do it for A2 and A3. This is what it would look like. And finally, it's the same thing I do for A1 and A0. So I, again, sort of took my 6 bits of input, treated it as 3 chunks of 2. Each one of those pairs I fed into a 2 to 4 decoder. And now I have, from each decoder, I have a 4-bit output. So I have a total of 12 bits at this stage, corresponding to the 4 bits of Z, 4 bits of Y, and 4 bits of X. Now what we do is, we are going to AND 1 bit of each of X, Y, and Z to generate an output. So what I mean by that is the following. Remember, I need 64 possible, I need 64 outputs corresponding to different one-hot codings. There are 64 possible one-hot codings for the big decoder. And they basically correspond to different combinations of this. So let's look at, let's say I do the following. B of I make it into let's see. So let me see if I can present it as an example. Let's start with this. Okay. So what I do is I took my A, I fed it into these 3 decoders. I got these 4 outputs, and now I'm going to select all possible different permutations that might be happening. So let's say I saw Z0 is high, and Y0 is high, and X0 is high. If that's the case, then my input would be A5, A4, A3, A2, A1, A0 being all zeros. And that corresponds to one particular combination. I could look at Z1 is high and Y0 is high and and Y0 is high and X0 is high. So I have 4 possibilities in Z, 4 possibilities in Y, and 4 possibilities in X. So if I were to select one from each, I have a total of 64 possibilities. 4 choices in X, 4 in Y, 4 in Z. Each one of them corresponds to a different value of A. So when A was all ones, that corresponds to saying Z3 is high, and Y3 is high, and X3 is high. Likewise, let's say I was interested in A being 1, 0, 1, 0, 1, 0. Then that corresponds to saying Z2 is high, and Y2 is high, and X3 is high. So all possible 64 combinations we will try. In circuit terms, that looks like, as shown in the next slide, that I have 64 AND gates. They have 3 inputs each, and with that I cover all possible combinations where I take 1 bit from Z, 1 bit from Y, and 1 bit from X. And that would cover all 64 possible input values out here, because Z is covering 2 of the bits, Y is covering 2 of the other bits of A, and X is covering 2 of the other bits of A out here. So by using this 2 to 4 decoder together with an army of AND gates, I'm able to now create a 6 to 64 decoder. So I'm decoding 2 bits at a time, and then I'm selecting all possible 64 combinations that might occur out there. So let's say A was 0, 0, 1, 1, 0, 0. Let's try that. So let's say A520 was 0, 0, 0, let's say 0, 0, 1, 1, 0, 0. Let's say it's this guy. So A5, A4 is 0, 0. So out here, among these 4 wires, the 0th bit would be high. Right? A3:2 is 1, 1. So in the middle one, which bit would be high? So A3, A2 is 1, 1. So I'm getting 1, 1 out here. So which Y would be high? Y3, Y2, Y1, Y0? Y3, right? Because we are seeing 1, 1 out here. And finally, A1, A0 is 0, 0. So in the Z, Z0 would be high. So what would happen is, when I feed this input value, we get X0 to be high, Y3 to be high, and Z0 to be high. And the corresponding AND gate, the AND gate which was taking in Z0, Y3, X0, which would be one of these 64 gates, its value would be high, everything else would be 0. And same thing for other input patterns that would occur. So taking a bunch of simpler gates and kind of simpler decoders and then tying them together using an AND gate and do the trick. I could play the same game if, for example, if I had given you a 3:8 decoder. Let's say I had given you a bunch of 3:8 decoders, and I were to ask you, can you create a 4:16 decoder? What would you do? So my strategy in 2-bit decoders was I was decoding chunks of 2 bits in my input space. So now what I want to do is I want to design a 4:16 decoder, but this time around you are given 3:8 decoders. So let's try that. So again, I want to design 6 to 64 decoder given 3:8 decoders. So I have 6 input bits, and I can only decode 3 at a time. So our strategy would be, I'll take A520. I'm going to split it into 2 chunks. One would be A5 through 3, and the other would be A2 to A0. I'm going to feed it to a 3 to 8 decoder here, and I'm going to feed it into another 3:8 decoder here. How many bits would I have at the output of 3 to 8 decoder? Anyone? How many out? 8, right? Right there in the name, right? So we'll get 8 here. We are going to get 8 here. Let's call this thing X, X720, and let's call this guy Y720. And what I'm going to do is I'm going to create AND gates. So I have a bunch of AND gates, and which are going to take one wire from X, one wire from Y. How many AND gates would I have? 64, because I have 8 choices of X, 8 choices of Y. So I will cover all the combinations, so 0 through 63. Okay, and they will correspond to the 64 outputs that I needed. And now what would happen is, given any particular bit pattern on A, one wire on X would be high, one wire on Y would be high, and the corresponding AND gate would result in a high output. The remaining AND gates would all be 0. Okay, so the basic idea is, if I were to have a simpler decoder, I can always gang them up like this to create more complicated decoder. Back to our 6 to 64. Let's say I were to give you one 2 to 4 decoder and another 4 to 16 decoder. Do you think you can use them to create 6 to 6? So the strategy there would be, I'll take 2 bits, feed it to a 2-bit decoder, 4 bits, feed it to my 4 to 16 decoder, and again play the same game. Okay, so I can always construct a bigger decoder in terms of smaller decoder, as long as the number of inputs in the smaller decoders add up to my inputs that I need for a decoder. So I decode kind of different things.
Can you explain why there's 64 ADHDs?
Do you agree that, do you agree that 3 to 8 will give me 8 outputs here, and 3 to 8 outputs here? Okay, and what I'm doing is, I want to create as many AND gates as are possible, where I pick one input from X and one input from Y. There are 8 wires in X, there are 8 wires in Y, so there are 64 choices. Okay. Whereas previously, in the previous slide, I had X, Y, and Z of 4 wires each. I was picking one from X, one from Y, one from Z, so 4 times 4 times 4. So, so that's the strategy out here. So let's talk about advantages. What did we gain by doing this? Could we have simply, like I keep telling you that, hey, the tools are great, they can do this stuff for you. What are the advantages of doing this divide and conquer strategy? big decoders and simpler decoders. So let's think about, let's say you were to be designing 6 to 64 decoder using the direct approach. I make the gigantic truth table. It would have 64 entries, and then I can, for each one of the 64 outputs, I can basically pick the corresponding minterm. So I can basically, for each output, I can create a normal form representation. What you would see is that in that case, I will need 64 6-input AND gates, right? One for each one of the 64 outputs. I would need a gate like that. That's a total of 384 inputs. And I have previously said that the cost of a circuit is roughly proportional to the number of total inputs that exist in the circuit. So I have 64 gates, each with 6 input. So the number of, the total cost of the circuit is 64 times 6, or 384. That is if I had done a straight array implementation. I would have created a truth table, and then for each one of the 64 outputs, it would correspond to one of the midterms. If I use a 6 to 64 decoder using 2 to 4 decoders, well, I need 12 2-input AND gates corresponding to the 3 2 to 4 decoders. Remember my 2 to 4 decoder, if you go back, my 2 to 4 decoder had 4 AND gates. Okay, and I needed 3 2 to 4 decoders, so I need a total of 12 AND gates. 12 2-input AND gates, that's 24 inputs. And then I needed 64 3-input AND gates here. So that is 192 inputs. I add them up, I get a total of 216 inputs. So a significantly cheaper circuit than a direct approach where I would have used 64 6-input AND gates. So cost is an advantage, but in engineering nothing comes for free. So what am I losing? There's always, you optimize one thing, there's something, Speed. So why is that?
Because you're going to have to do one more gate before.
Right. You are going through 2 AND gates now, right? You are first going through the AND gate in my 2 to 4 decoder, then I'm going through another AND gate. So I'm going through 2 AND gates. Likely in general, it would be a slower circuit than going through a single AND gate. So speed versus area, or speed versus dollar, or speed versus power. So when you design these things, you are dealing with these multiple optimization dimensions: power, speed, dollar cost, and perhaps other things. And anytime you're designing, it's always a trade-off between these things. So what I'm getting with this is A, a simpler design perhaps, but B, a smaller design, but at the cost of a speed. Any questions on this one? Is it clear to everyone what is happening out here? That why this new circuit, this circuit which we were using 2 to 4 decoder is slower than just a direct implementation.
Professor, why is 12 2 input and 64 3?
Okay, so that's 12. Yeah, so 12 2 inputs are because we have 3 2 to 4 decoders. Each of those 2 to 4 decoder had 4 AND gates. So that's why I have 4 times 3. So I should have written like 4 times 3, which is resulting. So this one is 4 AND times 3 2 to 4 decode. Okay, so that's what's happening out there. One other thing you notice, I didn't count inverters in this thing. And the reason is that usually in circuits, it's often the case that if X is available, X bar is also available. That's how kind of things are often designed. So, so we tend to say that there was no cost in getting that to begin with. So, a reasonable first order assumption when you're doing these kind of analysis. So this breaking down into simpler decoders and then doing it in terms of that results in a cheaper design and is arguably easier to design. I can just reuse parts, but can be more, but it's more, it's slower because it has to go through multiple levels.
So it's always like most efficient to use the smallest decoders.
Could you say to me?
It's always best to build it. Well, not best, but more efficient to build it out of like the smallest decoders.
Yeah. So again, I was saying that depends on what you are optimizing. Okay. If you are worried about area, then this is a good strategy. But if you are worried about speed, then make a direct implementation. Any other questions? Okay, so divide and conquer can have advantages, and but then in some other dimension they kind of. Okay, now decoders I said are used in a lot of places. Okay, so certainly they are used to select something, but it turns out that actually decoders are also a great way to implement an arbitrary function. Okay, and the concept is like the following. So what's happening? Let's say I give you a 3:8 decoder. So a 3:8 decoder, which you see at the top left, is taking 3 inputs and it's giving me 8 outputs, one of which is going to be high depending upon what my input value is. One way of thinking about it is that a decoder is telling me which minterm is, what minterm my input corresponds to. If input is 0, 0, 0, output number 0 is high. If input is 0, 0, 1, output number 1 is high. If input is whatever 1, 1, 0, output number 6 is high, and so on and so forth. So what a decoder is telling me is which row of my truth table is the input line. The current value of the input, which row of the truth table it is. And previously we saw that I can always express a function as an ORing of minterms, right, of its minterms. So I can write a function in normal form. So I can take a decoder and out of these 8, I can pick the minterms that I need and feed it into an OR gate, and I will get my logic implementation. So let's say I want to implement the function is prime. And again, is prime and 1. So we are counting 1 as a prime in this case. So I take minterm number 1, 2, 3, 5, 7. So I basically pick up those lines out of my decoder output, feed them into an OR gate. I have my is prime function. You want to implement, I don't know, is even function. Well, what I'll do is I'll take 0, 2, 4, and 6 and feed them into an OR gate and be done. Someone else needs a different function, they can do the same thing. So with a decoder, together with an OR gate, I can implement an arbitrary logic function. And this strategy works great for creating logic which has large number of inputs. So if I wanted to create a function which has 6 inputs, I'll use my 6 to 64 decoder. On the output from the 64 wires, I'll select the wires which correspond to the minterms of interest, feed them into an OR gate, I have my implementation. So it gives me a general way of implementing logic functions. So decoders, therefore, are a powerful tool. And in fact, there are chips available where all they do is they give you a bank of decoders and a bank of OR gates. And those OR gates are special ones. You can wire them up to be 2 input OR gates, 3 inputs, 4 inputs. So you can basically decide how many inputs those OR gates have. Basically what they have is they have a little fuse sitting at the input. And so you can blow the fuse and convert a 3 input OR gate to a 2 input OR gate. You disconnect one of the inputs. Okay, so what these chips have is they have decoders and they are wired into OR gates which have a large number of inputs but fuses at the beginning. You blow the fuse to disconnect some of the inputs. Using those chips, you can implement arbitrary logic functions. And they are go under various names. They sometimes are called programmable logic devices. Sometimes they're called programmable logic arrays or programmable array logic or FPGAs, a whole bunch of names. But deep down, what they have is these decoders together with some way of implementing this OR gate with an arbitrary number of inputs. And then you blow fuses at appropriate places and you are done. So decoders, very powerful, not just for their native decoding functionality, but they're also very powerful as a general way of implementing logic, so that you can create these chips, which now you can create in high volume, and people who need to create different kind of designs, they can basically program them on their own, as opposed to you having to manufacture them. So they give you kind of like software-like programmability. You get the chip when the system starts up, or perhaps at manufacturing time, you kind of blow the fuse or sort of set some switches, so to say, in the switch, in the chip, and you get your logic. So that notion of making hardware programmable by the end user is kind of a powerful one, and decoders kind of are part of the story of making that happen. So I can implement arbitrary logic gates. That's nice. Okay, so
Why not just implement your function using the midterms?
right, but the thing is that I need to know the function, right? So the idea is, let's say you want to create a chip which implemented a function whose midterms you knew. You have two things. You can go to a factory saying, give me a chip which only implements that midterm. And but the problem then is you have to give all that one-time cost which goes into making a chip. Okay. Versus if the factory says, you know, I have made this chip, you can implement your function, you can implement your function, you can implement your function, then you are all sharing that cost. So it becomes a cheaper design. Okay. So it's a standard game in engineering that there is, whenever you're designing a product, there is a one-time cost, or there's a design cost, a cost which is a fixed cost, and then there is a per unit cost. Larger the volume of a product, the fixed cost gets amortized over this. Okay, so if you are a small customer, you are going to be making a product and you're going to make only 10 copies of it. It's just not worth your time, worth your money to kind of pay someone to design a special chip just for you. You would rather use a chip which others are also able to use, so that you benefit from that cost. It's called non-recurring cost. Okay, so recurring cost refers to cost associated with every unit you make. Non-recurring cost means cost which is shared across all the units you make. So design cost is an example of non-recurring cost. Tooling cost, right? I mean, setting up the factory, that's an example of a non-recurring cost. On the other hand, silicon cost, the material that you are using to make the chip, is a recurring cost. Testing a chip before you're shipping, packaging it, those are all recurring costs. So it's basically that game. So you would like to avoid having to create, if possible, chips or hardware which is custom just for you, because it will increase your cost. Any other question? Okay, so let's see how we are doing time-wise. We still have, 15 minutes. Okay, so next module, encoder. Encoder is, as the name suggests, inverse of a decoder. So what it would do is, it will take one hot and convert it into binary. That's what we need to do. So encoder is a logic module that takes one hot signal and outputs binary encoded signal. So for example, a 4 to 2 encoder would do the following. It will take, when the input is 0001, the output would be 00. When the input is 0010, output is 01. When the input is 0100, output is 10. When the input is 1000, output is 11. Okay, so what's missing in this table? Is it a complete truth table? No, right? How many? I have 4 input bits, so I have 16 possible input values, but I have given you the output specification only for 4 of them. So what would you do? So let's say I give you A3, A2, A10 to be 1100. What should the output be? What should it be? 0, 0? Well, so if I output is 0, 0, and the input is 0, 1, 1, 0, how do you know that input was 0, 0, 0, 1 or that incorrect input? So there's a tricky thing. I mean, it depends upon what you want. Okay, so so one thing is you can say, you know, all I'm doing is I'm making an encoder. You are supposed to give me one hot coded input. If you are giving me input other than one which is a valid one hot code, all bets are off. Output could be anything. Okay, that's another way of saying it. I don't care. Another one would be the one you are suggesting. You could say output would be 0, 0 if the input is incorrect. Another possibility is that maybe I can have an extra signal as an output indicating whether the input was valid or not. These are all possibilities depending upon the thing. Oftentimes, it could indeed be what you are saying, that the output for incorrect input, output would be 0, 0, and so that's kind of the default output. So it's an incomplete table, and but assuming that we basically don't care about what happens for incorrect input, then looking at this, you can say B1 is basically these two terms. So B1 is basically saying A3 or A2. If A3 is high or A2 is high, then B1 should be high. And B0 is A3 or A1. It's saying if A3 is high or A1 is high, then B0 is high. So that's my encoder, a 4 to 2 encoder. Now let's see what would it do if, let's say, input was 1, 1, 0, 0. Well, for 1, 1, 0, 0, A3 is high, A2 is high, A1 and A0 are 0, 0. So we'll get B1 equal to high, B0 equal to 0. So we will get the third row out here. And even though my input was invalid. But the thing is, I have more input possibilities than output possibilities. So something is going to go somewhere. And so this kind of logic is basically saying, if you supply me incorrect inputs, all bets are off. Anything could be high, so you should not supply that. Now, why do you think an encoder might be useful? The decoder we saw some uses. What do you think encoder is? Okay, so I can transfer. So I may have data in one hot coding. I need to get it across to a faraway point. Instead of sending one hot coding and using a lot of bandwidth, I can treat encoding as a form of compression and send it back. So that's valid. What else? Any other reason that I might okay, I want to do arithmetic with the numbers, and usually in my computers I do not have adders and multipliers and all for one hot coded stuff. I do have it for regular binary, so I move it to regular binary, do my arithmetic, and then maybe kind of go back. So that's and to kind of take the first point that you made, besides bandwidth, it could also be storage. Maybe I'm getting kind of a lot of data from 1-bit sensors, and only one of them is going to be high at any given point in time. I basically use it to convert to binary before storing in memory. So also reasons that this encoder might be useful. So from a circuit point of view, a 4 to 2 encoder is pretty simple. A couple of OR gates, so that's easily done. Now, as you might imagine, we would play the same game of designing larger encoders from smaller encoders. So now we know how to design 4 to 2. We just saw that, a couple of OR gates. Now let's say I want to design a 16 to 4 encoder. It's going to take a 16-bit one hot coded input, and it needs to generate a 4-bit binary number representation of it. So So what's happening is I have A0 through A15 as my one hot coded input. I want as an output a 4-bit binary number B0, B1, B2, B3. Okay, so now to make this happen, I will need a slightly special form of input for the 4 to 2 encoder. So what's happening out here is the following. Each one of these boxes is a 4 to 2 encoder. It takes 4 bits and outputs a 2-bit number out here corresponding to this one. The problem I have is the following. There's still an ambiguity, which goes back to something we were discussing earlier on, that what if my input is invalid? What would happen, right? So we didn't really have a satisfactory answer for that. Now let's imagine, so remember here the A's are all one hot coded. That means one of these 16 A's is going to be high, the remaining 15 A's are going to be 0. That means 3 of these encoders are going to have all zeros as input, which is an invalid one hot code. And somehow I need to know that. Somehow I need to know that this thing is receiving an invalid input. And for that, we have these encoders output an additional signal, which you see in these red colors out here. And all that is doing is it's basically saying, did I see a 1 or not? That is, did I see a valid one hot code or not? So what we are doing now is we are going to take these lower 2-bit inputs and feed them into a couple of OR gates. So this symbol is a little bit ambiguous out here. What you see out here is this is an OR gate. It is taking 4 2-bit inputs and outputting 1 2-bit output. What it really is it is 2 4-bit OR gates. One of them handling, let's say, the bit number 0 from each one of these 4 pairs, and the other OR gate is handling the other 4 bits. So this really is 2 OR gates. One which is outputting B0, the other which is outputting B1, and each one of them is taking 4 1-bit things. So this is a shorthand notation the book uses, Logisim also uses, that when I say I have a n-bit OR gate, it really is n OR gates running in parallel on different bits of the process. Okay, so now back to out here, what's happening is the blue signals are feeding into this OR gate, and this OR gate is basically saying that is any one of these high, and the top one is saying which one of these clusters is seeing something. So I'm kind of doing the top 2 bits are basically saying that does the 1 lie in the top group, so second from top, third from top, fourth from top. So this 4:2 encoder is going to encode which one of the 4 groups did my input 1 lie in, and that's what it is doing out here. And this guy is basically saying within that group what is happening. So let's try out an example. Let's say A11 was high. So if A11 is high, what do you think I would see on the output, the blue output of this 4:2 decoder? So I would design my decoder. So it is this encoder. Top encoder is seeing all zeros because only A11 is high. So what will happen out here is that so this is seeing 0 0 0 0, this is seeing 1 0 0 0, this is seeing 0 0 0 0, and this is seeing 0 0 0 0. What will happen is our encoder is designed such that we see 0 0 here. Here we see that the highest bit was high. So here I would be seeing 1 1. On this one I will see 0 0. On this one also I will see 0 0. And the output here what will happen is I'm doing an ORing. So I'm going to see a 1, 1 out here. So my lower 2 bits are 1, 1. Now remember, this is A11. So what would I expect on the encoded stuff? This is the 12th bit, right? So I would expect to see a value of 11. What is 11 in binary? Anyone? What's 11 in binary? 1011, right? So I would expect output to be I would expect the output to be 1011. So the lower 2 bits are 1, 1. That you see we are getting. Okay. Meanwhile, what will happen is on the red one, since this guy saw a 1 hot code, so it will output a 1. The rest are not seeing a valid 1 hot code, so they are going to output 0. So now this 4:2 encoder is seeing 0, 1, 0, 0. So it is seeing input number 2 to be high, and therefore it would output a 1, 0 out here. And those are these 2 bits. So this encoder is outputting the upper 2 bits, and this bunch of 2 OR gates are outputting the lower 2 bits. And I designed my encoder such that on the red output, it outputs a 1 only if it sees a valid 1 hot code. Otherwise, it outputs a 0. And moreover, if it sees an invalid 1 hot code, on the blue output, the encoder would output 0, 0. So these are special encoders which have some additional logic thrown in to kind of generate this red signal also. And that lets me kind of gang them together in this particular way. So we're going to stop out here. I'm going to pick this up again, but sort of TAs will also go through it.